What I'll do now is I'll hand over to Phil.
So just before I dive into the actual screen demos, just some basic details about the system. We are running on the Orquestr8 framework. So it's the same framework we use to build out our automation systems. We also use it to build out this PIC product. It's a modern microservices-based software. It's hosting agnostic, so we can run it on local machine. We can run it in the cloud, Azure, AWS, etc., or we can run it in internal companies on cloud hosted, etc. It works by interfacing directly with the WMS, either mostly in a machine-to-machine sense, so that there's communication is between our system and the WMS to do the optimization piece. There's 4 API calls necessary to make the integration, so it's relatively light in terms of integration. And basically what we're doing is we're taking the picking workload from the WMS, the details of what items need to be picked from where in the warehouse for each particular order. And we are working with those orders to optimize and produce a pick list, send it back into the WMS so that the actual pick list can then be executed in the current process within the WMS, so with your handheld terminal or whatever existing way that you're doing your picking. So I'll start looking at some of the particular areas in the system. I'll give you a quick overview of how it would integrate with your particular warehouse and some of the benefits we get out of it. Probably one of the first places that we'll take a look at is the layout screen. Now, you can think of this layout as a digital twin of your warehouse. So basically anywhere in your warehouse where you've got storage, be that organized storage from in aisles and mezzanines, etc., or even if you have less organized storage like runs of pallets, etc., in open space that you pick fast moving goods from, etc. All those elements get recorded in this layout. The layout is accurate down to about 1 centimeter, and then we use a network of nodes that basically link all of the different shelves and pallets, etc., within the warehouse, and we can use that to find the fastest route between any 2 points in the warehouse and get the distance involved in moving between those 2 points. They're obviously essential for the optimization piece we do in understanding how much distance is involved in any particular movement in the warehouse, and we can use that to get a total distance for the pick list that we're optimizing, etc., to find the best route to power that choice of best route. So one of the things we'd be doing if setting up with you is we'd be taking whatever layout diagram we can find for your warehouse, or sometimes a DWG drawing or something similar, overlaying that with the information of your aisle names and shelf names, etc., to get this demo layout, to get this layout complete as part of the system. One of the things that we would be doing with you, so the system takes over clustering for your picking purposes. So the tasks that come over to us are not yet clustered into their different types of picking. And we use a clustering engine within the system to actually identify, based on the orders that are coming over, we look at the dates, the types, any identifying features of those orders, and make a decision over how that order needs to be picked. So it's, for instance, is that an e-com order? Is it a single order, different to say a multi-line order? Is it a retail replenishment order? Are we picking into totes? Are we picking into cages, etc.? All of those decisions can be made using these clustering rules. One of the advantages of these clustering rules over the kind of standard rules that you see in WMS systems is that this is a no-code system. You can come in here as a user or as an administrative user, and you can make changes to these very quickly. You can test them, you can save them, and you can start running with them immediately. We can also have multiple rule sets available in the system, so you could have 2 rule sets, maybe if you're running a different set of rules for daytime picking to nighttime picking, or maybe midweek picking to weekend picking. Or even just a special rule set that comes into play during peak because of the increased number of people and the increased workload. That kind of thing you can do very easily with this system without getting someone in modifying the code of your WMS. So it's quite a useful area of the system. What it helps us do is take those workloads that are coming in, identify the type of picking that we're going to be doing, and link that to a specific physical type of picking. So, okay, this order is going to be an ecom single, and we're going to pick it in a bathtub with another 100 similar single orders, etc. All that is specified through this clustering piece. Once we've run that clustering rule set, what you'll get is a set of the individual picking profiles that are available in from that clustering rule, and it comes into this dashboard. So currently the system can operate in two different ways when we're looking at how to release work. We can do a wave response model where which we typically use for retail orders, where a large collection of orders are allocated over to the system in a wave, and in response to that wave, the system will generate all the optimized pick lists necessary to complete all the picking in that wave, and then that gets sent back immediately to the WMS system. So there's no manual intervention on the breathe side or no operator intervention on the breathe side. That data comes over, gets optimized, and gets returned as a set of pick lists back to the WMS, so that the WMS can then execute it. The other way we can run the system, which we more typically use for ecom pick lists, is that we build up a pool of orders in the breathe side. So as an order arrives in the WMS and is allocated a picking location in the warehouse, that order is then transferred over to us via the API, and it sits in our pool and builds up ready to the point that your operatives are ready to release work. So you've now got a new shift started, you've got maybe 4 or 5 pickers working in a particular zone, and you want to start releasing new work for those pickers. You can come in here and you can see the order well, you can see how many orders are sitting there, how many lines that is, how many units are involved in completing those orders. An estimate of how many pick lists that would be necessary to actually complete out those orders. And you can release work either at the profile level, so you could just start releasing all your work for, in this case, ecom multi. Another thing you can do, the system supports or understands the priority of orders. So when trying to use the system, we want to get a balance of the optimization piece, but also with your operation requirements. So we're not just saying these are the best pick lists, go away and work on it this way. We are still always trying to keep an eye on what is necessary for the operational requirements of the warehouse. So we can concentrate on things like the ship by date of orders, any particular priorities coming over from the WMS system that identify orders that need to be processed earlier. Maybe you've got next day deliveries where the pickup's at 4 o'clock in the afternoon that you need to get them processed as soon as possible. Maybe you've got VIP orders. We see orders for influencers and review sites, etc., requiring to be processed as soon as possible so that they go out with a sort of VIP service. So things like that, we can take into account all of that when releasing the work from the system to make sure that the operation requirements are met, as well as optimizing the pick lists. When those pick lists are released, the two primary benefits that I think Dan referred to earlier are all about reducing the distance walked. So the whole sort of initial benefit of this system is trying to reduce the amount of distance that your operatives walk when completing a pick list. The two key ways to do that are through what we call spatial batching, which is choosing the right orders to go together. And then the other way we do that is through optimizing the pick walk for each pick list. Now, here in the demo system, we have this particular screen to try and make it easier to understand how the spatial batching piece works and where the benefits come from. So we've got about, I think it's 200 orders in this demo system that we use for this batching piece. And what we've done is we've generated pick lists in two different ways. A FIFO approach, which is first in, first out. So basically, your standard WMS, when it's looking to release orders onto a pick list, firstly, it'll look at things like the ship by date and the priority, etc. But once it's gone through the more obvious priorities and ship by date, etc. It's going to put those orders onto a list just based on the age of the order. So the first 10 orders that came in will go together onto a pick list, and then the next 10 orders that came in will go on the next pick list, and so on. And that's what we're looking at here with these FIFO lists. So we generated these lists on the side here, 9 lists generated by the age of the order. And then on the other side here, we've got 9 lists that are generated based on our spatial batching algorithm. So looking at which orders go well together to reduce the overall walking that you'd be doing to complete those pick lists. Now, we can look at these visually on the layout here. So what we've got is the layout of all the shelves, etc., in the warehouse, and you can see a lot of coloured dots on here. Now, those coloured dots represent the picks that are necessary to complete a particular pick list. Now, you can see at the moment this is looking quite messy, quite chaotic. And if I look at an individual pick list in this set that have been generated FIFO, so basically by the age of order, we're pretty much covering the complete zone to complete that pick list. So we're walking through every aisle from the beginning of the warehouse to the end of the warehouse to actually complete this particular pick list. Those orders covering the whole of the warehouse, and similar in some of the other ones, you can see again that there's quite a lot of spread, there's quite a lot of aisles that have to be visited to complete that pick list. If I look at our spatially batched ones, if I look at all of them to start with, what you should be seeing here is almost like a rainbow spread, a much more ordered collection of colours, which indicates, helps us understand that what we can see here is when we've switched to our spatial batching, each of these pick lists is now covering a much tighter area within the warehouse, in this case only 2 or 3 aisles, instead of crossing the whole warehouse. And that sort of focus on only completing the area of the warehouse that's absolutely necessary for that pick list is where a lot of the initial savings come from. So you can see that in total, when following the 9 pick lists in the FIFO batching, the first in, first out batching, we're covering just over 6 kilometers to complete that set of 9 pick lists. So it's the same collection of orders, same number of pick lists, but over 6 kilometers. In the spatially batched equivalent, again, the same set of orders, again, 9 pick lists, but overall distance required to complete that is now only 3.6 kilometers. So, you've saved over 2.5 kilometers from that, just reorganizing the way orders are put onto the pick list. And it's probably over 40% saving in distance just from choosing the right orders to go together onto the pick list. And that's one of our primary benefits, is this spatial batching. On average, across a retail and e-com mix, we see somewhere between 50 to 55% savings in distances from that overall. The second bit I touched on was the routing element. So once we've chosen the right orders to go together onto a pick list, we then look at all of the shelves that need to be visited for that pick list and find the right sequence, the best possible sequence to visit all of those shelves. Now, usually in a WMS system, they'll follow a serpentine approach where you're literally sort of traveling up one aisle and then down the next aisle and then up the next and follow in a serpentine pattern. And there's nothing necessarily wrong with that. It's a quick and easy way to generate a route from a list of locations that's visited. But it's not the fastest way to get through the warehouse. It's not the shortest way to get through the warehouse. So in this example here, we've got, you can see for this pick list, all the red squares are shelves that need to be visited for the pick list. There's a green square to indicate where the trolley would be, an empty trolley would be picked up from, and this red square at the bottom is where the full trolley would be dropped off from. So you can see the route, the serpentine route, which the WMS would have created, is going to take us as far away as possible into the warehouse. It's going to drop us down in, and then it's going to start us picking the pick list following the route upwards. Then we're going to drop down into the next aisle. Then we're going to come across the bottom, and we're going to come up into this aisle collecting as we go, dropping back out before finally visiting the last pick location and coming down and completing the route. Now, it looks relatively reasonable. You know, there's nothing about that that looks like you're wasting a lot of distance in completing that movement. That route is about 436 meters in that serpentine sequence. If we now look at the optimized route produced by the braid system, we've saved over 100 meters and without doing anything particularly complicated, just by changing the sequence that we actually start visiting those locations. So we come in across the top, we drop down to pick up the first location here, move across, pick up us on our way down. Now, we'll then run across the bottom, pick up these two while we're down at the bottom before making the final loop up to the top, and then drop down, completing those picks and closing out the pick list. Now, what this system is basically doing here is trying to avoid the back and two motion and the vertical motion through the aisles. And just by making that change in the sequence, there's over 100 meters saving, which again, I think is about 27% of a distance saving. Now, this is probably a nice, simple example. Obviously, the pick lists can get a lot more complicated than this, and the routes that save can get a lot more complicated than this. But this example is sort of easy for the human mind to understand where the savings are coming from. These savings stack on top of the spatial savings. So when we're looking at that spatial savings previously, that was over 40% saving from choosing the right orders. And then on top of that 40% saving, there is another 30% saving again in the way that we've now optimized this loop. So this is how the two main distance-based savings of the system stack together. On top of that, there's a lot of elements in the system that focus on trying to make reduce the overall number of pick lists that you have to complete to get your orders picked. And you know, some of the ways we do that is we look at volumetrics. So we look at the right choice of picking container for orders. So one of the things we might do in e-com, say, is we might look at the size of the order volumetrically, and we can either work with multiple different sizes of container to try and get more orders on a pick list. So we might have large orders go on like 8 containers on a trolley, might have medium that go on 16, and we might have small that go on 32 containers in a trolley. One of our customers is actually running up to 64 e-com orders on a single trolley. And the other way we can do it is through something called dynamic dividers, where rather than having different tote sizes, you have the same size tote, but that the user is guided to place dividers in the tote so that large orders can take the full size of the tote, but then you can split the tote down using those dividers up to 8 ways. So you might now have 8 orders in a tote. And the advantage of that is that rather than taking out 8 pick lists to complete a collection of orders, you can suddenly complete those orders in just 2 pick lists because you are able to stack so many more orders in the same pick list. Things like that help to reduce the overall number of pick lists, and it just means that you're getting really dense orders, the most number of units possible per pick list, and that starts to give sort of secondary benefits in productivity. The other thing that we can do with that volumetrics piece is if you're dispatching, picking directly into dispatch containers like cardboard containers going out to retail stores, etc., then we will also optimize to reduce the number of cardboard containers that are going out, and those are again additional benefits that the system can drive in direct savings against the cost of shipping and against the cost of container use. And usually, you know, we see all those as benefits on top of the ROI that we've calculated. We'd usually calculate the ROI just on the distance saving. So anything that comes from the productivity benefits of reducing the pick lists or from the savings, direct savings that are coming from those shipping cartons and shipping costs, they tend to be like sort of additional benefits. We've got one customer running at the moment that they get back nearly 60% of their monthly cost from those direct benefits before looking at the benefits they're getting from the optimization. So, you know, they can have quite a significant effect as well as the distance saving.